Since the 1990s, I've had a sideline of looking at climate models, the science side of climate from sort of a data analytic perspective, and I'll show you some of that in a minute. But when I went down to Washington and I served on the CEA from 2012 to 2014, I had the energy portfolio, which was at a time that the president wanted to take some serious action on climate because Waxman-Markey had failed in his previous term. This action was all through administrative procedures like administrative authority through the Clean Air Act. So I spent a fair amount of time doing work on the Clean Power Plan, which was the regulation for the power sector, and on other areas of climate policy, and I'll talk about some of those in passing. So I got quite interested in the topic. I decided it was important. I thought, gosh, my graduate students are better than I am at proving theorems in econometrics, so why don't I do something useful? And I've been spending more than half my time in this area since then. I'm going to start with some climate change basics. So I think this is, it's kind of tough because some of you probably know a great deal about this and some of you might know less. But I'm going to start with where I started from, which is just what do the data say. So I'm just going to take a quick look at some of the data and hopefully in a way that is informative. Okay, so here's just a picture of what temperatures have been since about 1860 in global mean temperatures. So they vary, from place to place. You can see that before like World War I, they were pretty constant. They started to go up around the 1930s. They were constant until about the 1970s or 80s, and then starting in around 1980, they've been taking off in a serious way. Temperature rise has been about 1 degree Celsius since the late 19th century. A starting point in understanding this is thinking about what I'm going to spend a little bit of time on the climate science here, of only a little bit, and I'm going to do it from an econometrician's perspective. A natural question is what's causing this? Now, one approach to what's causing this is, maybe some of you have heard this phrase, 97% of climate scientists agree that this is anthropogenic, and for some of you, that's probably going to be good enough. But for others of you, that might actually set off alarm bells, and it's like, you're not totally persuaded by people who say, hey, I am from MIT, I've got a model, trust me. So if you fall in that latter camp, I'm going to do some really simple stuff. So the basic starting point of climate science is just an energy flux concept, which is that the temperature on the surface of the Earth is proportional to the energy flux that's hitting it. And so that energy flux comes from a couple of places. It can come from the sun, or it can come from radiation, warm body radiation from the Earth that is then absorbed and re-emitted back to the surface of the Earth by greenhouse gases. And so those are the two sorts of radiative fluxes. Here's what those radiative fluxes look like. So I'm going to go from the top to the bottom. The top is the radiative flux from carbon dioxide. It's called radiative forcing. That's the jargon. So it's the history of radiative forcing over this period of carbon dioxide. Forget about the green dotted line for a second. The one that's next below it is the radiative forcing from methane, which is also a greenhouse gas. Below that, the gray line is the radiative forcing from trace gases such as hydrofluorocarbons, which are really potent. There's not many of them, but they're very potent greenhouse gases. The wiggly line is solar insolation. It's radiative forcing from the sun. And so it's wiggling around because of sunspot cycles. And then it's kind of interesting, the negative line is from sulfur oxides. Sulfur oxides actually have the opposite effect. What happens is sunlight hits them, and because of their spectral characteristics, they re-emit it. They basically block the sun's radiation and bounce it back back into the atmosphere, back into space. So they have negative radiative forcings. The sum of those things, which is aggregate radiative forcing, is there in the dashed line. So here's a project that I did back when I just got started. I said, okay, so the theory is supposed to be that radiative forcing is related to temperature. How does that work? These things have trends. We know how to handle trends. So back using data from 1994, I did some co-integration stuff and some other stuff, sort of time series modeling of the time, and then just fit a trend. So here's the trend from that we fit back a long time ago, back in a paper that was, because of referee torture, wasn't published till 2006, but it was estimated through on data through 1994. And that's the underlying trend. I want to stress that red line is only a function of the radiative forcings. There's no temperature in that red line. This is just a fitted value based on the radiative forcings taken from table 2 of this paper. And the nice thing about this is, since it was fit on data through 1994, you've got 20 years of a true out-of-sample experiment. So one question you might ask is this theory any good? Like, how much should we put any weight on this at all? Does this seem to have any predictive content? And there's 2 interesting episodes in this out-of-sample period. One is that long flat period there, starting around 1998, which is called the hiatus. That's been used as arguments why we haven't, don't have any climate change or whatever. The other is then right after the hiatus, this thing really bumped up. So the question is, how does this work? So if I take that thing from table 2 of this, that was our preferred specification in this 1994 data set, that's the predicted value. Okay, so this predicted value is just based on radiative forcings, and those radiative forcings have this remarkable feature that they track the hiatus. Well, the reason for that is twofold. One is that the solar insolation are kind of in a sunspot low, and the other reason is that there were a lot of coal plants built in China that started emitting sulfur oxides in that period, and the sulfur oxides in that period subdued the warming effect of the increasing CO2. So anyway, it seems to fit pretty well. If you'd use this model, then ask the question, which is a common question, which is how much of warming is anthropogenic, you can actually back out how much is anthropogenic, because you can look at the solar component of it, that is the natural component of it, and you can hold the other greenhouse gases constant at their pre-industrial period averages, and you can estimate what the contribution is of the solar, of the natural component, and then the residual is the human, is the anthropogenic. So here's the natural component of solar warming, of global warming, and you can see that it tracks the predicted really well during, up to about 1920, but starting about 1920, there's this divergence, and then that divergence really goes in spades starting around 1980. So the answer is, how much of solar, by the way, I should say, we haven't used, there's no global circulation models in here, there's no supercomputers in here, there's like a co-integrating regression, and then some really basic stuff that everybody accepts. It's basically almost all anthropogenic. Okay, so I don't know whether, I find this supportive. For me, this is helpful and persuasive in terms of thinking about, do I really believe those MIT guys with their models? And the answer is, it turns out I do. Okay. So a question then is, if CO2 is really what's driving this, it doesn't give you some facts about CO2. Here's the history of CO2 in the United States. I'm now going to focus on the US, which is what I understand best. So this is CO2 in the US, and you can see that CO2 peaked in 2005, and ever since then it's been declining. There's a narrative associated with this decline, which is that, well, you know what, we've actually really turned a corner. And the reason we've turned a corner is because of energy efficiency, and people are aware of the problem of greenhouse gases, and we're doing a lot of things along those to mitigate that, and we have more fuel efficient cars, and so forth, and that and renewables are becoming more and more cost effective, so we can put solar photovoltaic panels on our roofs and so forth. So we're on our way. That is a popular narrative among environmentalists who want to say that it won't cost very much to eliminate, to deal with greenhouse gas, to decarbonize the economy. It's a popular narrative on the right because they'll say markets are solving the problem anyway. And it's a popular narrative among the green finance community because they say, we don't care if there's any climate policy, we've got a great product for you to invest in. Unfortunately, it's wrong. What's really happened, you will not be surprised, I bet everybody in this room can take a guess as to why the big drop was in 2009. What you might not know is that after that we had this, remember there's this fracking thing and cheap natural gas, and what's happened is that a lot of the coal plants have closed, the inefficient coal plants have closed, and now we're using natural gas. Well, if you take those factors into account, what's the future look like? This is what the U.S. Energy Information Administration thinks the future looks like. It thinks that we're basically going to be in the same place unless we do something, unless we change policy. A business as usual thing is that all of those paths in energy efficiency and renewables and so forth are going to be offset by economic growth, and emissions are going to be roughly constant. Emissions being constant means that concentrations are increasing. If you use estimates like we saw before, oh, here's some really short-term estimates. So this is something I just have been doing with some graduate students. Here's some short-term estimates. The impact effect of these emissions over the next 10 years during those 10 years, so this is a really short window on a global scale, is an increase of 0.13 degrees Celsius. So the long-term effect is much bigger than that. What's really striking about this is that there's meaningful quarter of a degree Fahrenheit, meaningful impact effects of global emissions at the current rates, even over a very short human lifetime. What are the consequences of these? Well, I think you've probably seen a lot of the sort of the scare stuff, so I'm just going to show, I'm not going to go through any of that. I'm just going to show you one interesting set of maps. Oh, I'm going to talk one thing, the one thing I'm going to, I should say that this temperature increase has generated some great data. So there's a large literature documenting what the effect of this warming is on crops, and what the effect of it is on even asylum applications, and on political stability, and on consumption, especially consumption among poorer countries, and not surprisingly, it's not so terrific. So what I am going to show you, I'm just going to show you one thing, which is something related to sea level rise. The sea level, water expands as it gets warmer, so the sea level is going to rise. That's one reason. Another reason for sea level rise is the glaciers will melt, and maybe a little bit of ice sheets will melt too. So I'm just going to illustrate. It's kind of here's an interesting illustration. Okay, so this is a map of where we are. So you can see. I don't know if I can actually, if there's a pointer here. I don't think, probably don't want to touch the wrong thing. Can you see where the SNEST is? It's like, the SNEST is, you see where the SNEST is? Sort of? This is, yeah, directly up from the blue dot. Oh, those blue dots, if you go there, it's great. You can click on it and they'll show you the Hatch cell or Harvard University or something. This is produced by NOAA, National Oceanographic Administration. That's the current map. You can see Harvard up there in the corner near the bend of the Charles, and then MIT is down there in the middle. And maybe oh yeah, so okay, can you see that? Is that working? No, I'm not getting, all right, doesn't matter. It turns out sea level rise isn't uniform, and it depends on local gravity, but also on local currents, and it happens to be the case that the Northeast is a place, even if sea level rise is about 70 centimeters or 90 centimeters, which is a business as usual scenario by the end of the century, it turns out that's like almost maybe 1.5 times, maybe even twice as much in the Boston area. So sea level rise here by the end of the century in a business as usual scenario might be 1.5 meters. This is what 1.5 meters looks like, which MIT is not doing great. Littauer Center is in good shape. Littauer Center is becoming beachfront property. Harvard's recent investments in Alston, those don't look so terrific, I have to say, for those of you who know this map. Now, I don't think this would actually occur because all that this is that those are regions that are actually below sea level. But of course, lots of the world has places that are below sea level. So you could keep that water out by building sufficient dams or dikes. If you start to see more severe, what are called abrupt irreversible events, that could change the situation. So if you start to see, say, partial melting of the West Antarctic ice sheet, or even very partial melting of the Greenland ice sheet, that could increase it by a substantial amount, many, many, many meters. If you even go from 1.5 to 3 meters, this is what 3 meters looks like, and I think that would be much harder to mitigate. So you can imagine trying to solve problems like this by building dikes and so forth, but that is, I think, like literally just like throwing money in the ocean. and certainly not like the most efficient way to proceed, probably. So with that, let me switch gears and let me talk a little bit about costs and policies and approaches. So, so first of all, let me just remind you that there's a number of externalities to address. It's not just the carbon pricing externality. There's also a research and development externality. For certain aspects, there's going to be a network externality. So, for example, think about electric charging stations and electric vehicles, sort of a chicken and egg deal. And then there's other externalities that one can think about as well. But those are the three that I'll be keeping in mind. So let me summarize my bottom line. Okay, so the conventional wisdom in the profession is that by far the most important element of a suite of climate policies is a carbon tax. My own view is that we also need to take technology-pushing policies very seriously, and more seriously than we have been. This view is informed by positive political economy, what politicians seem ready to do, by empirical evidence, and by some key success stories, and by a small but insightful literature on carbon prices, R&D subsidies, and induced technical change. Here I'm thinking of recent research by Doron Asimoglu, Philippe Aghion, Heidi Williams, Van Reenen, Akajit, Stancheva, Melitz, Lemoyne, and others. And I'll come back to this at the end. The usual measure of the cost of a climate policy is something called the social cost of carbon. What the social cost of carbon is the monetized net present value of the damages from emitting a marginal ton of CO2. The estimate there is the 2016 estimate under the Obama administration. It's about $50 a ton. There's a lot of evidence, there's a wide consensus that this number has got an enormous standard error and a lot more research is needed. There's a big research program going on with resources for the future. There's people involved there's a big involvement from the Chicago group, from Michael Greenstone's group in Chicago. There's a big involvement from Saul Sheng and Marshall Burke's group in Berkeley. We've even got some time series econometricians from Princeton putting their shoulder to the wheel on this one as well. So, but for now, I'm just going to use this $50 per ton. Okay, so now I'm going to talk a little bit about policies. Climate policies in the U.S. fall broadly into four categories. So the first is what I was working on when I was in the Obama administration, which is regulatory approaches. I'd argue that we put a lot of thought into the Clean Power Plan. Clean Power Plan was pretty efficient. It would have reduced emissions by a meaningful amount at quite an inexpensive value. Estimates are like $11 per ton. Other regulations are not as efficient, so there's a big literature pointing out inefficiencies in the corporate average fuel economy, or CAFE standards, which regulate mileage in automobiles. There's an awful lot of things about that design that really cry out for improvement. Costs for those can be anywhere in the $50 to even $300 per ton, depending upon the estimate and exactly what's going on. A big problem with regulatory approaches, beyond just the potential cost and the cumbersome, is that they actually have pretty limited scope. You just aren't going to solve the climate problem only through regulation. There's other problems too. They're not durable, so all of the regulations that I worked on have all been reversed by the Trump administration. And moreover, at least in the United States, if the authority is Clean Air Act authority, it's very unlikely that the Supreme Court, with the most recent appointments, is going to be sympathetic to an expansive interpretation of the Clean Air Act. So my view is that basically the regulatory approach is off the table, so we need to think of other approaches. The second approach, which we've had a lot of experience on, is, I don't know what you could call it, but maybe the sort of I'll call them narrowly focused policies. And so examples in this include weatherization programs, mandates to use certain renewable fuels in our fuel supply, state-level renewable portfolio standards, and other things like that. The costs of these policies are all over the map. There are a few cases, like putting corn ethanol in the fuel supply up to 10%, that I would actually argue is a negative cost policy. It's something that's done by the market without any need, but that is really the exception. If you look at biodiesel, for example, that costs between $150 and $420 per ton, a lot more than that $50 per ton, depending upon how you treat the incidence of the biodiesel tax credit. These policies also have the problem that they interact in sort of complicated and typically just expensive but not very effective ways with other policies. So by and large, these sort of narrowly defined policies are not ones that, that economists tend to think are very efficient or effective, and at best are a small part of a broader package of solutions. The third set of policies, which we don't have in the United States, are economy-wide carbon pricing policies. Now, although efforts for cap and trade did fail with Waxman-Markey, other countries have adopted a carbon tax, and so it's worth thinking about what those costs might be. The dominant tool for analyzing a carbon tax is for analyzing the costs and economic macro effects of a carbon tax, or computable general equilibrium models. A recent example of that is a book last year by Larry Goulder and Mark Hafstad, where they examine a variety of carbon pricing models and carbon pricing policies, including a carbon tax. For a lump sum transfer tax, so it depends how you recycle the revenues in terms of the economic effects, but for a lump sum recycling, which is the framework considered by the Carbon Leadership Council and supported by that letter that probably many of you signed that Janet Yellen spearheaded. For that, they actually find pretty darn low costs. So for a $20 carbon tax that increases at 4% per year, they estimate that that takes a hit to GDP of 1% over the period between now and 2050. So that's like roughly speaking, or 2050. So roughly speaking, that's like 3 or 4 basis points per year. So that's a very small hit to GDP. In work that I'm doing, because some countries have actually adopted a carbon tax, you can actually ask empirically what's the effect on their economies. And so I'm doing some work on that with Gib Metcalf, and so far we can't seem to find any measurable effect. Actually, our coefficients are positive, which doesn't make any sense, but they're not statistically significant. So that's consistent with this small effect that Goulder and Hafstad estimate. The thing about a carbon tax, though, and we think that that's clearly a very efficient policy, I think it's important to remember that it's a limited policy, and some people who don't know a lot about the way that the energy works in our economy might not really realize this. A carbon tax at low levels will essentially decarbonize the power sector, and it will certainly get rid of all coal in the power sector because coal just becomes too expensive. But a $20 carbon tax is 20 cents a gallon, and nobody's going to go out and buy a bunch of EVs just because gas has gone up by 20 cents a gallon or even by 50 cents a gallon. It takes more than that to really transform the transportation sector, and it takes even more than that to make any serious dent in the other third of the economy, which is buildings and commercial and residential. So a carbon tax has a big effect at first, and then it kind of peters out. So then the question is, what are you going to do with the rest of that? And that gets me to the final set of policies that we have investigated here in the United States, which is these technology pushing policies. I mean, basically the storyline of this family of policies is induced technical progress. So it goes under a number of other terms, learning by doing or moving down the cost curve and stuff like that. But basically it's induced technical progress. I'm going to give you 4 examples. 3 of them are success stories. I would argue success stories, although this is anecdotal. And one of them, it's also anecdotal, but it is definitely not a success story. And so I think there's policy design issues that we can learn from there. So the first of these policies is photovoltaics. So there is a big push in Germany through the Energiewende program and their net metering program, or their feed-in tariff program, which is like net metering. There was a big push in the California Solar Initiative, and then starting around 2008, we introduced a income tax credit for purchases of solar panels to put on your roof. And between all of these programs, there was really a big big increase in spending on solar photovoltaics. Well, what has happened is that solar photovoltaic panels have really come down enormously in price to the point that they're actually, in some applications, like out in the deserts in Arizona, cost competitive with natural gas and with other fossil fuel generating facilities. Now, the thing is, you should be thinking to yourself, so what he just told me is that the price went down and consumption went up, and somehow that's supposed to be this like great insight that's going to solve the energy economy. And I think that this basically points to the identification problem in empirical studies of induced technological progress. There's a little bit of work that gets at this, so there's a nice paper by a guy at Cornell, Todd Girardin, who gives some pretty solid identified empirical evidence that learning by doing and that this demand pull concept made a difference in the price coming down, but a lot more work needs to be done. I'll give you a second example. The second example is in battery electric vehicles. So here too, there's been very substantial demand pull policies that have been trying to stimulate production and consumption. And essentially what you see here, the main driver of battery electric vehicle costs is the battery cost. And essentially what you see here, I've plotted a frontier, which is marginal, the range on the x-axis, and the price, the MSRP on the y-axis. And what you can see is that over time, this frontier is marching to the right. Which is to say, you're driving farther for cheaper. And we're now getting to the point that the Chevrolet Bolt, which is my car, is really quite a cost-effective vehicle. Now, there's implicit subsidies behind that because of the subsidies under the CAFE standards, and also there's probably some plays for market share that are driving sales prices below marginal costs. So I think you can't take these literally as estimates of marginal cost, but it's pretty clear what the pattern is. An important driver in this has been subsidies through the income tax credit and through regional, which amount to $10,000. At least for me, I got $10,000 back when I got my Bolt. Those are substantial subsidies, and I think those play a role. There's no research at all documenting that. I think that this would, in terms of like getting the supply and demand and identification right, and I think this is a really great topic to study, incredibly important in this area. And a final one is wind. And you see, offshore wind is a market that simply wouldn't exist. I mean, it simply wouldn't exist if it weren't for like crazy policies that required you to go buy this expensive thing. And what's happened is we've seen that the wind towers have gotten bigger and bigger. They've gotten more efficient. It's gotten cheaper to install them, and the prices have gone down and down and down over time to the point that they're almost cost effective. A slide I don't have is a big failure, which is second-generation biofuels. The policy there, the renewable fuel standard, failed to give reliable support, and I think we can learn a lot from that policy. I studied that policy in considerable detail, but I'm not going to go into it here. Okay, so let me just make a final comment here. So I think so if we think about now what's the revealed preference among politicians, so doing a little tiny bit of positive political economy, we've actually had substantial programs that have pushed these major technological things forward. We aren't able to have a carbon price. I don't see a carbon price on the horizon. We've tried 2 times to get a carbon price, once through Waxman-Markey, a second time through the Clean Power Plan for that sector. Both of those have failed. There is substantial pushback. So just from a political economy perspective, the programs that seem to be the most effective and that politicians are willing to support are these technology pushing programs. I think we cannot underestimate these political economy considerations. So there's a substantial vested interest in existing capital to not see success in this area. Multiple large oil companies, including Exxon and BP, officially endorse a carbon tax, yet those companies teamed with other companies to spend $30 million to defeat the recent Washington State carbon tax initiative. I mentioned that a key reason for the failure of the renewable fuel standard to develop second-generation low GHG biofuels was its programmatic uncertainty. Well, that programmatic uncertainty, to no little extent, was due to ongoing litigation and lobbying by the refinery industry. So this isn't surprising, but understanding it is important to assess what climate policies might be feasible going forward. So let me just conclude by saying that from my perspective, the most important papers in the environmental economics literature are actually by macroeconomists, one of whom is leaving right now, and who are not really in the environmental economics field. There's a lot more work to do. Policy is moving quickly and improving our understanding of the design and effect of technology pushing policies in this area could have a really big payoff.